Arduino. Founded in Italy 20 years ago by a group of visionary educators and engineers, Arduino was born out of a desire to democratize electronics and make them accessible to everyone. Named after a bar in Ivrea, the platform started with hand-assembled circuit boards for students at the Interaction Design Institute Ivrea. The founders, Massimo Banzi, David Cuartielles, David Mellis, Tom Igoe, and Gianluca Martino made key decisions to keep the hardware and software open source, ensuring that anyone could learn, create, and innovate. The result is a world where anyone, regardless of their technical background, can create electronic projects that once seemed out of reach. This is the world that Arduino has made possible. The significance of Arduino extends far beyond its technical specifications. It has lowered barriers of entry, making electronics affordable and accessible. Its massive open source community fosters sharing and innovation, sparking the maker movement and encouraging creation over consumption. Arduino has become a platform, bridging disciplines like art, design, engineering, and computer science, and enabling rapid prototyping. Its impact is felt in education, product development, and the philosophy of technology accessibility. Arduino has inspired a global movement, empowering hobbyists, students, artists, and professionals to bring their ideas to life. It has influenced modern IoT and smart devices, proving that with the right tools, anyone can be an innovator. Arduino's choice of the AVR ATmega 168 and later the ATmega 328P microcontrollers was pivotal. These microcontrollers offered a balance of performance, cost, and ease of use, featuring 8-bit architecture, flash memory, SRAM, EEPROM, and built-in peripherals like timers, ADC, PWM, UART, SPI, and I2C. This made them ideal for a wide range of applications, from simple projects to complex prototypes. What happens next is anybody's guess, but the frontiers spawned by the Shockleys and Moores of the world, with their advanced education and access to vast amounts of capital, are giving way to the kid in their bedroom, tinkering with a board and a laptop, intent on building a thing, turning their imagination into reality through simple advancements in integrated circuits, sensors, and open source software. How can microchip technology fuel the ethos of the do-it-yourself maker movement? Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience. Our guest today is Bob Martin. Bob is a senior applications engineer at Microchip Technology, but we know him more familiarly as the Wizard of Make. He joins us today from his home office in Northern California. Welcome, Bob.
Thank you very much, Dana. Pleasure to be here, and always good to talk, always happy to talk about this ecosystem that I'm deeply, deeply buried into.
We're excited. We're going to get into it. Thank you for joining us on Beyond the Microchip. In the intro, we briefly talked about Arduino and the maker movement of the last 20 years or so, and Microchip has a unique place in that saga. What can you tell us about it?
Yes, interestingly enough, you mentioned the choice of the, first off with the 168, the AVR 168, and then the 328P. At that time when Arduino was shopping around, it was... And the makerspace, which I'll get into later, right, on how it all grew. It was almost a perfect storm, fortunately, for us. The 168 and its family, what we call the classic AVRs, brought forth not only an incredibly efficient design in 8-bit. The AVR was a master's thesis for two gentlemen that were going to NTU Norway, Alf Egil Bogen and Vegard Wolin. And rumor has it that's where AVR came from, Alf and Vegard's RISC. But
okay,
that's, yeah, it hasn't been confirmed, but that's the that's the running theory. Okay?
We are not above urban legends here.
Yes, so that is the urban legend. And this design of the AVR, they did something unique that no other microcontroller vendor or anybody that was architecting microcontrollers did at the time. They went and talked to compiler vendors, the GCC community, IAR, Kyle, anybody that wrote a C compiler, and it said, here's a proposed design. What would you do to make it even better to fit in a C compiler? No one had done that before, because the manufacturers like, Motorola and Intel and whatever, they were going at what was probably the most power efficient, what made sense from a pure hardware point of view, and you got what you got in the instruction set, which resulted in an instruction set and architecture that made it incredibly efficient for C compilers. So some of the C compilers kept their secret sauce to themselves, but came back to Elf and Vegard and said, hey, here, change these instructions a little bit, which made it incredibly easy for the GCC community to come up with a really high performance C compiler in a very short period of time. One of the gentlemen that actually helped develop that C compiler used to work for Atmel. I knew him, and he did a lot of work on it. But at the end of the day, one of the key linchpins was Arduino, again, back to the democratization. You wanted inexpensive development tools. I was weaned on 8051s and 68 HC11s, and way back when Intel had just introduced the microcontroller, and a lot of those development tools were, to put it straight, like really expensive, right? It locked you out of the hobby space.
And they were on the x86 architecture?
Yeah, and the x86 architecture, you could, Microsoft gave you good free compilers, but it was the embedded part, because you were running, I was also developing embedded x86 architectures, but when you don't have MS-DOS running there, you have to do a bunch of magic to make the code run, because it's the operating system that takes care of all the memory management and fills in spots that isn't in a normal hello world that you're running on MS-DOS or Windows or whatever. So the compiler, there was a completely open source GCC compiler that was in those days, and still is, very high performance. So completely open source, that met one of the criteria. The other thing, besides all the peripherals that you mentioned, the UARTs and the timers and the I2C and whatever, was the fact that flash microcontrollers were just popping their heads out of the sand. And what I mean by flash microcontrollers, the older crowd listening to this podcast will remember the OTPs, the one-time programmables, or those funky ceramic chips with the little windows that you erased with a UV oven. I did the majority of my microcontroller work, what seems like another lifetime ago, with about 12 of those just rotating in that UV oven. So I was smelling ozone all the time when I was doing early development and embedded with the 8032s and 8031s.
OTP kind of says enough for the younger crowd too, is that this wasn't rewritable, right?
I was, when I first started with National Semiconductor, we had it was an inexpensive development kit, but we shipped the kit with two or three OTPs. And if you're just learning, it's real easy to go through all three of those parts in a weekend and go, I'm done now. I actually convinced National to make a windowed version of this part, because I said, people aren't going to be ordering 100 of these parts just to get their software.
One chance to make a mistake.
One chance, and all you need to do is flip a semicolon, or a 6 turns into an 8 or something like that. You're done. So the flash allowed, again, reprogramming without having to wait 20 minutes or without having to buy a $25 or $35 part that had the windowed UV. And there was another significant advance over the flash parts, is these parts could program themselves.
Ooh.
Right? So that meant if you fed it the right thing, like through a bootloader. And the other part of the equation was the 168 and the 328s allow you to section off a part of that flash and load in a bootloader. And then when you erase the rest of the flash, you can leave that bootloader sitting there. So it was unmutable memory in that instance. So that met all the criteria that they were looking for perfectly. So now you could have this flash microcontroller that was, again, fairly inexpensive. You could write some software, and through the serial port, now you could download software, and the only thing you needed between you and that development board was a USB cable.
And is that where this succeeded, where others failed?
Yes. So that was one of the important parts of it. So it was the implementation. They were working on various implementations, but they had that vision. It was definitely the easy access to a trivially inexpensive development system. So then on the other side of the equation, the part of the other success was this whole ecosystem, the whole system, again, from the, Massimo and Tom and Gianluca and Dave, they were all educators. All previous attempts at making inexpensive microcontroller development systems were from manufacturers who were trying to sell their product rather than focusing on getting people to learn how to do them or to learn how to use these microcontrollers.
Right.
So it was a different approach from the beginning. They also backed that up with a whole bunch of the support ecosystem, the website, and at that time the user forums. So you were completely cocooned, for lack of a better term, in a very responsive, supportive development system. So you had the ease of use of the development platform. Again, all you need is a USB cable and one of their boards. You had free software to download, and you had a whole community behind you that grew very quickly.
And these boards weren't that expensive, right? What were they, $5 to begin with?
No, they were around the $30 mark, but still,
by comparison.
By comparison, Motorola came out with the 68HC11. I remember it was a big push into the universities way back in the day in the late 90s, and that kit was $68.11. And that was an unheard of low price for a kit. The problem is you were spending a little more than $68.11 to get into, for the development tools and things like that. I once paid $10,000 for an Intel development kit for x86 that didn't work at all. So, yeah.
All right. So 50% off and easy to get into. Yeah.
And it just flew from there. So that was kind of the primary reasons. The 328, the peripheral load, or the peripheral set, we call them the 328, the YORT, and, the timers. I2C that started to grow out of, I2C was primarily made for temperature sensing on PC motherboards. And then it grew into memories, slow memories, or anything that just needed a simple, slower, in air quotes, 100 kilohertz to 400 kilohertz at that time, two-wire interface to get stuff, get information around from temp sensors and things that were slow. Then that also, I mentioned that kind of perfect storm. So it was the perfect storm of that technology and the microcontroller becoming available. And as that influenced the maker space, because around that time, and for those of you who are aware, Arduino just celebrated their 20th anniversary, which is it's been around for a while.
Just under a month ago from when we're recording this.
Yep. And there's some more perfect storms that were coming around. I'm going to cover three things here. As it fostered newer technology, drones. Back when all this was just poking its head out of the sand, the Arduino environment, there was a couple things that were happening in the model RC space. It was going from those two-stroke noisy engines right, with the nitrous engines, over to more efficient and more affordable brushless DC motors. And the actual AVR was part of that environment. This was hand-tuned code because driving brushless DC motors is not trivial to do it correctly. But there was a transition over from the from the gas powered to the DC motors, which allowed you to say put four on an aircraft, and all of a sudden you had the beginnings of a drone. And right around that time, like I said, just as I was poking the head out of the sand on this, I was working for InventSense. And InventSense was one of the pioneers of MEMS gyros and accelerometers. So that was all coalescing. Now we had small brushless DC motors that could spin pretty fast, but still drive a propeller. You had a inexpensive and very well supported development environment for microcontrollers. And then you had now inexpensive 6-axis IMUs. And that all coalesced into a drone, because you can't, when you're developing a drone, you just can't plot 4 motors on it and then send the same throttle signal to each of the 4 motors.
It's got to be able to balance itself, yeah.
It's got to be able to balance itself. There's a feedback loop there, or else it's just going to tunnel. Right. Plus, you have to turn, the rotors have to counter rotate so your thing doesn't rotate in the air.
It has to go forward, it has to go backwards, it has to go left and right, and it has to go up and down in 3D space. Exactly.
So you need those slight tilts, but you need that local feedback loop with the accelerometer and the gyro to go, nope, that's a little too far, pull it back. So that allowed the drone space to grow very quickly. Because now all these development environments not only the development environment, but the technologies, the motors and the IMUs. So drones started taking off, no pun intended or intended. I go take which direction you want on that one. And then on the other side, then 3D printing, because now you had this back to the Arduino community and the ease of use. And then one of the 328's bigger brothers, the Mega 2560, had more memory, but it also had 100 pins. And it's probably one of the largest pin count 8-bit microcontrollers that's been ever made. But that opened up the possibility to bring all these inputs and outputs, which is what they needed in a 3D printer. You needed the XY translation, you needed the extruder motor control, you needed limit switches. And although the 3D printer space has been taken over by the 32-bit stuff now, there are still legacy upgrade boards for the 3D printers that still are based on the 2560. You can still
remember at the time, so you're talking about a fused deposition modeling 3D printer, right? Those are pretty much where they started.
Yes.
And that was just a milling machine with no drill bit in it.
That was, and then they, the fused, and then the molten deposition, when they figured out they could make this stuff and melt it and slice it up and then punch it down layer by layer, right? Because a lot of the open source 3D printers still use G codes.
That's right.
And G codes come all the way back from the milling machine days, the CNC milling machine days.
Yeah, back to the 50s and 60s. Yeah,
exactly. When I started my career, I was working with a company, and we shared the space with the machine shop, and a lot of these guys were hand editing G code, with a text editor. Because these machinists knew the G codes. It's still around. People still complain about it, but no one's come up with a better solution yet. So, and then the other thing that came out of this, it kind of extended, was something called kinetic art. And that was one of the fascinating things. Because the Arduino language, they're called sketches. The origin of that language was actually wiring, and wiring was an easy to use language that was running on personal computers, but was allowing artists to do things like mix video or do effects or whatever without burdening artists to be able to control things. And so that kinetic art, where these people aren't electrical engineers, they're artists. I said, I'm going to hook this Arduino up, and somebody's told me how to hook this Arduino up to these pins. And here's like a 1/4 horsepower motor through a relay. And now I can make my dragon wings flap. Right. And I can make the eyes glow. And I don't have to learn a whole bunch of electrical engineering embedded concepts. I just need to go, digital write something high, and that motor turns on. Right. And I can go delay 600, and I get 600 milliseconds delay. And that begat that whole kinetic art thing where people kids started making animatronic costumes.
Yeah.
Right?
You get into cosplay, you get into robotic art. Yeah.
And then the other part of this whole perfect storm, and then right around that time, Del Doherty from Make Magazine's going, I'm seeing a lot of DIY stuff. Again, it's resurging. And then Make Magazine, and then the Ultimate Maker Fair. Well, not the ultimate, but like the huge Geek Fest, right? Mm-hmm. Like Burning Man for geeks showed up at San Mateo. I've been to every San Mateo / Bay Area Maker Fair since it started. And that's where, again, I saw the cosplay, the kids coming in with animatronic costumes or hats with the ears that wiggled or whatever. I saw that, the 3D printers and the drones come out of that space. And the other cool thing was, and I'm going to swerve over to kind of like, then, so it was the makerspace, and then the beginning was the education space, which we haven't really. I was talking about why it was successful, because it was designed by people that were trying to teach embedded electronics, mm-hmm. right? So it's already but become very popular in the education space. It was a practical, low-cost platform, and it was just overtaking, again, from, sinking down into the primary school levels, in the colleges and the high schools and whatever. But there was other weird swerve, not weird, it was nice to see, where in the industrial space, there was still a lot of distrust about a system that was so easy to use and so inexpensive, right? It blew a bunch of paradigms away. But where it was gaining traction without having to convince anybody was in the industrial space, where somebody wanted to create a mechanical, or a systems engineer wanted to create a test system. And he didn't want to spend a lot of money on, I won't mention the names of, there's companies out there that make incredibly robust and complete, but yet fairly pricey test systems. But if you just want to hook a motor that just presses a button for 300,000 times or 3,000 times, right? Then a test engineer, again, could, within the space of a couple days, literally just duct tape a test system together and put it on the test floor. When I was, this was about 10 years ago, I was giving a class on Arduino and advanced debugging techniques with Arduino. And a gentleman from a well-known household name, product name, I won't mention the product, but you all know it, came up to me, and he was a director of test engineering from the East Coast. He'd flew all the way out from the East Coast to one of my lectures, my classes in California at a trade show. And he wanted some more information. He said, Bob, this is what I want to do. I want to reduce the cost. We're spending millions of dollars in this test equipment. And I'm sitting there thinking, at the end of the day, the actuators are just simple relay blocks. And from what you've shown me on your demonstration code, I could get my engineers in the course of a week to write the same code. And I went, yeah, and you would save all this money. Right. So there's this whole, as it's inching in, the Arduino ecosystem is inching into the pro space a little bit. Arduino Meta is continuing to push that. But
this is where you're starting to get into rapid prototyping?
Yeah, exactly. This is, I just want to realize something. This is not going into production. This is helping me get other stuff into production by being able to implement a really simple, straightforward, and inexpensive test system. Where my mechanicals and my systems engineers down on the floor don't need to get allocation of time out of my software teams because they can just do it themselves. So it was, yeah, like I said, I've used the term perfect storm many times in this discussion, but it really was just the way things lined up with the Arduino, the drone motors, the IMUs, the affordable IMUs, and that precipitated all these other companies, or helped all these other companies like SparkFun and Adafruit to like grow, because all of a sudden there is a huge market for people that just want little breakout boards to be able to hook up to Arduino. Yeah. I'm going to try stuff. It was the concept of plug and play embedded development kind of grew out of that, right? And it's been phenomenal to watch, and it's still going, right? So yeah, it's been a wild, enjoyable ride right now. And then the ability, again, the open source, the ecosystem allows you, if there's people that are more skilled and embedded, you can mash together the Arduino system and what we call bare metal to eke that last drop of performance out of these parts.
Mm-hmm. This concludes part 1 of our 2-part episode on microcontrollers, makers, and the DIY movement. Join us next time as we pick up our conversation where we left off and get into 8 versus 32-bit, warranties are meant to be broken, and the future of Microchip's collaboration with the maker movement. Thanks for listening.